So, I was trying to explain this really dumb pun to a chatbot the other
Oh,
day.
yeah. How'd that go?
Not well. It was one of those like dad jokes where the whole thing hinges on a word having two meanings at once.
Mhm.
And the bot, it didn't get it. It
Uh-huh.
understood the syntax, it could define the words perfectly, but it just missed the flavor, the overlap.
That is the ultimate litmus test for artificial intelligence, isn't it?
Yeah.
Humor usually lives in those gray areas between definitions.
Yeah.
If you can't see the gray, you miss the joke.
Exactly. And it got me spiraling into this whole question of how computers actually, read. We sort of assume they look things up in a giant internal dictionary, pick definition number 3, and just move on.
Mhm.
But if I say, I'm going to the bank, the computer has to decide instantly, right, am I getting cash or am I going fishing?
And that is the classic bottleneck in computational linguistics. It's the context problem.
Hmm.
For you and me, the difference between a financial bank and a river bank is obvious. We don't even consciously process it. But for a machine, that ambiguity is a crisis. It has to make a choice.
Which brings us to the research we're unpacking today. We're looking at a really fascinating paper by Diana McCarthy titled Measuring Lexical Similarity via Substitutes, Translations, and Usage Judgments.
It is a seminal piece of work, a really foundational paper.
It really is. And the mission here is so cool because McCarthy is basically telling the whole industry, stop trying to force words into boxes.
Yeah.
She's arguing we need to move away from these rigid dictionary definitions and start looking at how words relate to each other in a more fluid, almost mathematical way.
Exactly. It's a huge paradigm shift from asking, what does this word mean, to asking, how is this word behaving right now?
Yeah.
And to do that, she uses 3 very human tools: paraphrasing, translation, and just, intuition.
Okay, so before we get to her solution, we have to really get the old way of doing things. The paper spends a good bit of time critiquing word sense disambiguation, or WSD. That's the standard approach, right?
It was, for a long time. Yeah.
Yeah.
You have a fixed inventory of meanings, usually from something like WordNet.
WordNet, right.
Think of WordNet as this superstructured digital dictionary. It lists every possible sense of a word and gives it a number: sense 1, sense 2, sense 3. Very orderly.
I've looked at it. It's detailed, almost like aggressively detailed.
And that's the catch. It was a catalyst for so much early research. But McCarthy points out this major flaw. The distinctions it makes between senses are often, well, arbitrary.
How so?
They were made by linguists sitting in a room deciding where one meaning ends and another begins. But language out in the wild doesn't always respect those borders.
And the paper has a great example of this messiness with the word match.
Match is a perfect case study in this kind of frustration.
So in WordNet, you've got sense 2, a formal contest, like a football match, that's clear. Then you have sense 8, a partner, like a married couple. And sense 9, something that resembles or harmonizes with something else.
Right. On paper, those look like totally separate buckets.
They do. But then you look at the real sentence McCarthy pulls from her data. It says, 26 weeks by the week in which the approved match with the child is made.
The approved match with the child. This is about adoption.
Right. Now imagine you're the computer. Which WordNet bucket does that fall into?
Well,
It's definitely not a football game.
Well-
So is it sense 8, the partner, the approved partner with the child? That sounds weird. You don't call a parent and child partners in that way?
no, exactly. Sense 8 implies a partnership of equals, a romantic or business thing. It doesn't fit the dynamic of adoption at all.
So, okay, is it sense 9 then? Harmonizing.
Yeah.
The parent harmonizes with the child?
It's closer, but sense 9 is usually about visual or aesthetic things like those shoes match your purse.
Or the curtains match the rug.
Right.
So we're stuck. This adoption match is somewhere in between. It's about compatibility, which is like sense 9, but it involves people and a legal bond, which is sort of like sense 8.
And that is the problem with the buckets. The meaning in that sentence falls right into the cracks between the definitions. If you force the computer to choose sense 8 or sense 9, you're technically feeding it wrong information either way,
A square peg in a round hole.
because you only have round holes available.
There was another example that I thought was even more contentious, the word child. You'd think child is simple.
You would think.
It's a kid.
But WordNet splits it up. Sense 1 is young person, sense 2 is offspring, regardless of age.
Okay, so the child played in the park is sense 1. I am the child of my parents, even if I'm 40 years old, is sense 2.
Simple enough, but then what happens when you translate it to French? In French, both of those concepts are covered by one word: enfant. So linguistically, are they actually different senses?
Or just shades of the same idea.
Exactly. And then WordNet throws in sense 4, member of a clan or tribe like the children of Israel.
Which connects back to offspring, but in a metaphorical collective way.
Right. And the paper points out that these senses form a web. Sense 1 pulls one way, sense 4 pulls another, but they're all kind of anchored to sense 2. Trying to group them into separate, discrete folders is just a subjective nightmare.
It's like trying to draw a hard line on a color spectrum. You can say this is blue and this is green, but eventually you hit teal.
Yeah, and the computer looks at teal and crashes because there is no teal bucket.
Precisely. And McCarthy's whole argument is, stop trying to draw the lines. Stop trying to label the teal. Instead, just describe the teal.
So how do we do that without a dictionary? This brings us to the methodology. She proposes using substitutes, translations, and usage judgments.
Okay.
She uses 3 different data sets. And the key here is that none of them use a predefined list, like WordNet. They're all unsupervised in that sense. They rely on raw human intuition.
Let's break these down because how they interact is really the core of her argument. So first, there's LEXSAB.
The English lexical substitution task. It's pretty much what it sounds like. They gave human annotators a sentence with a target word, say match, and just asked them to provide a substitute word that fits that specific context.
So if the sentence is the match was exciting, I might write game. If it's this shirt is a good match, I might write compliment.
Exactly. You're not picking a number from a list. You're just engaging your vocabulary. You're providing a synonym that feels right.
Okay, then the second one is CLLS.
Cross-lingual lexical substitution. Same idea, but with a twist. The annotators were native Spanish speakers. They looked at the English sentence and provided the best Spanish translation for that target word.
And the third one, which feels like the reality check, is USIM.
The usage similarity dataset. And this one is pure gut check. Humans are shown 2 different sentences with the same word. They just rate on a scale of 1 to 5 how similar the meaning is.
No definitions involved.
None. Just. Does mash in sentence A mean the same thing as match in sentence B? 1 is completely different, 5 is identical.
Okay, so we have paraphrases, translations, and similarity ratings. The hypothesis is that we can use the first 2 to predict the third.
That's the idea, yeah. The method is all about calculating overlap. The theory is, if 2 uses of a word share the same paraphrases, or they share the same translations, they're semantically close. The more overlap, the closer the meaning.
This is all a bit abstract until you see it in action. The paper has this incredible breakdown of the adjective stiff that really made it click for me.
Oh, yeah.
It's like a forensic analysis of a single word.
It's a great data set because stiff is one of those words we use all the time without realizing how flexible it is. They looked at stiff in 3 totally different contexts.
Let's walk through them. Scenario 1, a stiff heart. The context is medical wing, a heart muscle that isn't pumping right.
Right. So they go to the LAX sub P group, the English paraphrasers, and they get words like rigid, inelastic, and firm.
Inelastic is a very specific scientific word. Then they go to the Spanish speakers for the CLLS data.
And they get duro, tiso, and rigido.
Okay, keep those in mind. Now, scenario 2, a stiff punch. We're in a boxing ring now.
Or a bar fight.
The English substitutes shift. We still see firm, that's interesting, but now we see strong and hard. Inelastic is gone. You wouldn't call a punch inelastic.
No, that would sound ridiculous. And the Spanish translations shift too. We get duro again, it's a very versatile word, but now we also get fuerte, which means strong. We don't get tiso or rigido like we did for the heart.
Right, because a punch isn't physically rigid like a board, it's forceful.
Exactly. Now, scenario 3, a stiff image. This was describing a statue or a carving that looked awkward or unnatural.
The English substitutes here were stern, formal, unnatural, totally different vibe.
I mean, unnatural is a long way from strong. And the Spanish, duro appears again. It seems to be the Spanish equivalent of a Swiss Army knife here. But now we see forzado, which means forced.
This is where that overlap theory just shines. If I'm a computer, I don't know what stiff means in a human sense. I can't feel a muscle, but I can look at the list.
You can.
Firm connects the heart and the punch. They share a bridge.
But firm does not connect the punch and the image. And strong only appears for the punch. So the computer can calculate that the semantic distance between stiff punch and stiff image is greater than the distance between stiff punch and stiff heart.
And the Spanish helps triangulate this even more.
Ideally, yeah. Duro is the broad connector. It's like the supersense that covers all 3. But queso isolates the physical rigidity of the heart. Fuerte isolates the power of the punch. By looking at the intersection of these sets, You can map the word in a sort of 3D space.
You're creating a Venn diagram of meaning. You don't need to say this is sense 4. You just say these two usages share 50% of their substitutes, therefore they're 50% similar.
It creates a continuous scale of meaning. It captures the gradient. It acknowledges that the medical stiff heart and the boxing stiff punch are maybe cousins, but they're not siblings.
So that's the theory. Did the math actually hold up? When they compared this overlap score to the human ratings, that 1 to 5 scale, did it match?
It did. The correlation was highly significant. If the computer calculated a high overlap in substitutes, the humans almost always gave a high similarity rating.
Wow.
But there was a twist in the results that I found genuinely surprising.
The monolingual versus bilingual thing.
Yes. You might assume that bringing in a second language, Spanish, would help clarify things.
Oh, yeah.
You know, distinct words for distinct concepts. If English is a bit mushy, surely Spanish will cut through the fog.
That was my assumption. I figured translation forces you to be precise. You have to pick forte or tiso. You can't fudge it with stiff.
Right. But the study found that the English paraphrases correlated better with the human usage similarity scores than the Spanish translations did.
Wait, that's completely counterintuitive. Why would the monolingual list be better?
Because translation introduces noise. Maybe the translator isn't perfect? Or maybe the Spanish word duro is just as ambiguous as the English word stiff, so you're just swapping one ambiguous bucket for another.
Oh, right. If duro covers the heart, the punch, and the image, it doesn't actually help us separate them.
Exactly. Whereas with the English paraphrases, you get this much wider variety of synonyms: rigid, hard, inelastic, strong, stern. That richness provides a higher resolution picture of the meaning.
So the takeaway is huge. We can evaluate how well a computer understands a word just by asking it to find a synonym. We don't need a massive, expensive bilingual dictionary.
It's a huge win for developers.
Just teach the bot to paraphrase. But, I mean, surely this doesn't work for every single word. There have to be edge cases.
Oh, it absolutely breaks down. It is not magic, and the paper highlights what they call the trouble words.
I like the distinction they made between the good words and the bad words. The good word was fire, specifically the verb.
Right. Fire.b. Think about the meanings. You can fire a gun, you can fire an employee, you can fire pottery in a kiln.
Those seem pretty distinct.
They're very distinct. And the correlation for fire was incredibly high, 0.921. That's because the substitutes just don't overlap. You don't terminate a gun.
And you don't shoot an employee, at least not in the HR sense. So the synonyms just naturally sort themselves into neat little piles.
Exactly. The context makes it obvious.
Okay, so when the meanings are far apart, the system works perfectly. What makes a bad word?
The adjective special and the verb work. The correlation for special was abysmal, around 0.10, and for another word, neat, it was actually negative.
Negative. So the computer was basically guessing the opposite of what the humans thought.
Essentially, yeah. It was just random noise.
Why? I mean, what makes work so much harder than fire?
This brings us back to the human element. The paper discusses inter-annotator agreement, or IAA.
Which basically measures, did the humans agree with each other?
That's it, exactly. You can see where this is going. If I say the plan work and the clock works, and I ask 3 people if those are the same meaning.
You'll get 3 different answers. One person says, yes, they both mean to function. Another says, no, one is abstract success, the other is mechanical operation.
And a third person just gives it a 3 out of 5.
And if the humans can't agree, the computer has no ground truth to aim for.
Exactly. The low correlation for words like work or special wasn't a failure of the algorithm. It was a reflection of the fact that the concepts themselves are just slippery.
Yeah.
Special is a vague word. Work is a broad concept. They resist being put into boxes.
It reminds me of the word run. You run a race, you run a business, the fridge is running, your nose is running.
Yes.
They all imply some kind of movement or operation, but the overlap is just messy.
And that messiness is where the mid-range predictor comes in. This is one of the cleverest parts of the paper for me.
The mid-range predictor. It sounds like a statistical tool, but it feels more like a philosophy.
It's a brilliant little heuristic.
Yeah.
The authors looked at the mid-scores. They calculated the proportion of human similarity judgments that fell in the middle of the scale. A 2, 3, or 4.
The mezone, sort of similar, but not really.
The mez zone, exactly. And they found a direct link. Words with a high frequency of these mid-range scores always had low inter-annotator agreement.
Which makes intuitive sense. If everyone is voting 3, they're probably all scratching their heads.
But think about the application of that. If you're building an AI, you can predict which words are going to be nightmares Simply by looking at this distribution.
Mm.
If you see a word where humans constantly give these middle-of-the-road ratings,
You know that word has messy, interrelated meanings? You can flag it as a high-risk zone. Warning. The word bound is approaching.
exactly, and it suggests that for those words, trying to force a decision, trying to say, is it sense 1 or sense 2, is a fool's errand. The confusion is the meaning.
That is a heavy concept. The confusion is the meaning.
It really challenges the whole goal of natural language processing. For decades, the goal has been disambiguation. Remove the ambiguity, clarify it, make
Yeah.
it sharp.
Right.
But McCarthy's work suggests that for a significant chunk of our vocabulary, ambiguity is an inherent feature, not a bug.
We've gone from looking for the right answer in WordNet to accepting that the answer is often a cloud of maybes.
And that this cloud can be mapped mathematically.
Oh.
We validated that unsupervised methods, just looking at how words swap and translate, can accurately reflect that cloud. And that's crucial for things like machine translation.
Right.
If you want a computer to translate a pun or a poem or a complex emotion, it needs to understand the gradient, not just the hard and fast definition.
It needs to understand the teal, not just the blue and the green.
Precisely. We're moving from a world of hard borders to a world of continuous space.
So here's something I'm still chewing on. We talked about those mid-range scores, the 2s, 3s, and 4s. We usually treat those as data noise, right? We want the computer to be 100% sure. But if humans constantly rate a word like work as somewhat similar, maybe we need to stop asking computers to be more precise than we are.
And that is the provocative thought here. Perhaps the problem isn't that our algorithms aren't good enough to categorize the word. Perhaps the word itself refuses to be categorized. If ambiguity is central to how we communicate, if it allows us to be flexible and creative, then maybe we need to stop trying to fix it.
And instead,
We need to build systems that can live comfortably in that uncertainty.
living comfortably in uncertainty. I think that's a lesson that goes way beyond linguistics. It has been a pleasure dissecting this with you.
Always fun to look under the hood.
And to everyone listening, next time you search for something and get exactly what you wanted, or maybe something slightly different that turned out to be better, take a second to appreciate the messy, fluid, overlapping math that made it possible. We will catch you on the next deep dive.